Hello dear students and welcome to the course of Pharmaceutical Organic Chemistry 3rd. My name is Rahul Pandey and I am a faculty at School of Pharmaceutical Sciences, Swami Ram Himalayan University. So dear students, now we have arrived to the last unit of our course Pharmaceutical Organic Chemistry 3rd, which is named reactions, organic named reactions. You will going to learn what different named reactions are, how they are important to the field of pharmaceuticals and how they are applied and how different drug molecules are prepared with these named reactions. So not just learning the mechanism of this unit is important, but also you need to see how you can apply in different aspects of organic chemistry. So let us begin with this unit. Now we will study metal hydride reduction. So in this unit, in this topic, we are going to study a few metal hydrides, a few metals and their related compounds who are the source of hydride ion. Hydride means H minus ion, and they are responsible for reduction of many organic compounds. So the two main metal hydride reducing agents are NaBH4 and LiAlH4. NaBH4 stands for sodium borohydride and LiAlH4 stands for lithium aluminium hydride. But before getting details about these two compounds, we must first understand what reduction means in organic chemistry. So in organic chemistry, when you say the term reduction, it means there is a conversion of higher functional group to a lower functional group. For example, carboxylic acid is a senior functional group, as you all know from IUPAC nomenclature. When it is converted into aldehyde, which is a lower functional group, we call this process reduction. This is a reduction process. In the similar way, if this aldehyde group is converted to alcoholic group, which is a lower functional group, it is also called as reduction. When nitro group is converted to NH2, it is also known as reduction process. In the same way, an alkyne group is converted to alkene group. This is known as reduction process. And even when this alkene is converted to alkane, okay, this process again is referred as reduction. So reduction simply means the conversion of a higher functional group into a lower functional group. To convert this thing, to perform the reduction in organic chemistry, there are few reducing agents which are very famous and students should learn the names of it. So the names are, first of all, NaBH4. NaBH4 is called sodium borohydride. Okay, sodium borohydride. Next is LiAlH4. LiAlH4, it stands for lithium aluminium hydride. Lithium aluminium hydride. The third reducing agent is hydrogen gas in presence of nickel catalyst. Next reducing agent is hydrogen in presence of palladium and carbon. You can also use hydrogen in presence of platinum catalysts. And there is last a very famous reducing agent which is known as DIBAL. So diisobutyl aluminium hydride. So these are few common and frequently used reducing agent for reduction in organic chemistry. Now, according to the syllabus, we are going to deal with sodium borohydride and NaBH4 and LiLH4 in this lecture. Now, sodium borohydride and lithium aluminium hydride. NaBH4 is sodium borohydride, sodium borohydride, and LiAlH4 is lithium aluminium hydride. So these two are a very common reducing agents. The main thing that should be kept in mind is that these two are the source of H negative ion. H negative is known as hydride ion. Hydride ion, as because it has a negative charge, it can act as nucleophile, and it also acts as the same nucleophile in many reactions. These two, NaBH4 and LiLH4, as I have said, they both are reducing agents. However, if we consider the power or the reducing capability of sodium borohydride and lithium aluminium hydride, we will find that lithium aluminium hydride is a stronger reducing agent than sodium borohydride. And there is a reason behind it. To know that reason, we must first take a look on the structure of the both. Let us say we take sodium borohydride first, NaBH4. NaBH4 is basically made up of two ions, sodium ion and borohydride ion, BH4 ion. The structure of borohydride ion could be as follows. Boron is attached to 4 hydrogen atoms like this, and there is a negative charge on this species, and particularly on boron. Now, in the same way, if we take a look at lithium aluminium hydride, there is a lithium ion having positive charge and aluminium attached to 4 hydrogens, and aluminium has also got negative charge here. Now, as because they are source of hydride ion, I have already told that, so while doing reaction they have to give H negative ion, because they reduce via giving H negative ion to the molecules to be reduced. Now, if you take a look at the periodic table and compare boron and aluminium, you will find that boron is less metallic than aluminium. And because it is less metallic than aluminium, and you know that metal has a greater tendency to lose electron, because when this species will lose H negative ion, BH3 will be formed. Obviously, H will take away the electrons, BH3 will be formed, and H negative will take away the electrons as a hydride negative ion. For that, a bond between boron and hydrogen must break, and boron should give away its electron to hydrogen. In the same way, in lithium aluminium hydride as well, the bond between aluminium and hydrogen will break, and H negative will take away the electrons, and it will also form AlH3 and H minus. Now you know, I have already told that boron is less metallic than aluminium. It means there is a lesser tendency of boron to release H negative ion in comparison to aluminium hydride. So boron, as because it is not easily giving H negative ion, it will not easily reduce everything. So it means that NaBH4 thus becomes a weaker reducing agent than LiLH4. A stronger reducing agent will be the one which will release H negative ion faster. So obviously AlH4, LiLH4 is a stronger reducing agent because aluminium is a metal and it has a greater tendency to release its electron to hydride ion. So hence it will easily release. It will release faster this H negative ion, and hence it becomes a stronger reducing agent. Now let us move ahead and see these two reducing agents individually in detail. So now let us begin with LiAlH4, lithium aluminium hydride. So there are few points that a student at UG level must keep in his mind about LiAlH4. Number one, it is a powerful reducing agent. It is a powerful reducing agent. Point number two, when reacted with water, it reacts violently. So it reacts violently with water. So we have to be extremely careful during the reduction by LiAlH4. As because it reacts violently with water, the reactions of LiAlH4 are usually carried out in ether and THF, tetrahydrofuran like solvents. Water is avoided at all costs. Fourth point, we have to avoid a few reagents with LiAlH4. Number one is alcohol, ROH. We should avoid amines, which is RNH2. We should also avoid halogenated compounds like chloroform, dichloromethane, DCM or MDC, and we should also avoid strong acids. We should also avoid strong acids like HNO3, H2SO4, HCl while working with LiAlH4. Now, next thing we must all understand that what are the groups that are reduced by LiAlH4. As you know that LiAlH4 is a strong reducing agent, so it is more capable of converting or reducing a wide variety of organic compounds. So now we need to see which groups are reduced by LiAlH4. Okay. Number one is aldehyde, RCHO, which is aldehyde. A aldehyde when reduced by LiAlH4 gets converted into alcohol. If it's an aldehyde, it gets converted into 1 degree alcohol, primary alcohol. Now if you have ketone, it will get reduced by LiAlH4 to a secondary alcohol. So it's a 2 degree alcohol. If you have carboxylic acid, COOH. If you reduce it with LiLH4, it will get converted into 1 degree alcohol. Okay. But to add up in your knowledge, if we see for carboxylic acids, which is a better reducing agent? So the better reducing agent for carboxylic acid is B2H6. It is better than LiAlH4. for reducing carboxylic acid. Now, it also converts ester into alcohol. When ester is reduced by LiAlH4, both the parts of the ester, the acid part and the alcohol part, get separated into alcohols. So R CH2OH is one alcohol which is formed, and this R dash part also becomes a alcohol. So we get a mixture of alcohols when we reduce ester by LiAlH4. Now we can also reduce epoxides through LiLH4, and these epoxides will form alcohol. We can also reduce cyanide or nitrile by LiLH4, and it will convert it into amine. We can also reduce amide by LiLH4, and it will also get converted into amines. Even if you can try, you can also reduce alkyl halide to alkane by LiLH4. But there is a point that you must consider before doing it. Only 1 degree alkyl halide and 2 degree alkyl halides are converted into alkane by LiLH4. 3 degree alkyl halide cannot be converted into alkane through LiAlH4. Now let us understand it through an example. We are having this 1 degree alkyl halide, and it is converted with the LiAlH4 to an alkane, which is CH3CH2CH3. So 1 degree alkyl halide can be easily converted to alkane. But if we talk about 2 degree alkyl halide, it can also be converted. For example, if we are having CH3CH3, and if we try to reduce this alkyl halide by lithium aluminium hydride LiLH4, we can easily get CH3CH2CH3, that means alkane. But if you try to convert a 3 degree alkyl halide, say for example CH3CH3CH3 CCl by LiAlH4, it will not undergo this reaction and form alkane. Rather than it goes elimination, and it forms alkene. So this is a problem with lithium aluminium hydride. It will better form an alkene rather than an alkane with a 3 degree alkyl halide. So lithium aluminium hydride easily converts 1 degree and 2 degree to alkane, but it does not convert this into alkane. Okay. Now the last conversion is, you can also convert lactone, which are also known as cyclic ether, esters by lithium aluminium hydride, and you will get diol. As you know that in the previous reaction, you can easily conclude that when ester was broken down, both the parts were converted into alcoholic group. Okay, so here in the same way, ester is again broken down by lithium aluminium hydride, gets reduced, and thus both the parts become alcohol. So you will get two OH group on the same molecule, hence it becomes diol. So this is a cyclic ester. Cyclic esters are also known as lactones. So this was all about lithium aluminium hydride. Now let's move on to sodium borohydride. Now with sodium borohydride, let us see some of the important features. First of all, it is a weaker reducing agent than lithium aluminium hydride. Point number 2, as we have studied that lithium aluminium hydride reacts violently with water, that does not happens with sodium borohydride. So it does not react violently with water. Does not react violently. Third point is, you must consider, you can use water or aqueous alcohol, means an aqueous solution of alcohol, as a solvent, because it does not react with water violently with water. Water or alcohol can be easily used. So it's convenient to use sodium borohydride. You can also use 15% NaOH, sodium hydroxide, and decline as a solvent. But you must avoid using strong acids. So this thing is similar with lithium aluminium hydride. It's common to both NaBH4 and LiLH4. Now what are the groups that are reduced by NaBH4? So sodium borohydride, as because it's a weaker reducing agent, so it does not have a very wide capability to reduce organic compounds. Mainly it reduces RCHO aldehyde group to the alcohol. It also converts ketone to alcohol, particularly secondary alcohol. And now it also converts acid chloride. Acid chlorides are RC double bond OCl. It can convert this acid chloride into aldehyde, RCHO, acid chloride. It can also convert imine, RCH double bond NH, to amines, RCH2NH2. Okay, so these are the few functional groups like aldehyde, ketone, acid chloride, imines to alcohol 1 degree, alcohol 2 degree, aldehyde and amines. What organic compounds functional groups are not reduced by sodium borohydride? Sodium borohydride cannot reduce an ester. It cannot reduce an ester. It cannot reduce a carboxylic acid. Sodium borohydride cannot reduce carboxylic acid. Sodium borohydride can also not reduce an amide. Sodium borohydride is also not able to reduce a carbon-carbon double bond, which is alkenes. So these reagents, these organic compounds are not reduced by sodium borohydride. So as now you have understood, sodium borohydride is weaker, very weak than lithium aluminium hydride. So it is not capable to reduce these functional groups. Okay, now let us understand the mechanism through which lithium aluminium hydride and sodium borohydride reduce the organic compounds. If you will see, you will find quite a similarity between the two, between the mechanism followed by lithium aluminium hydride and sodium borohydride, but there is a little difference at the end. Okay, so let us start with the mechanism of reduction by LiLAlH4. Mechanism of reduction by LiLH4. So let us take an example where lithium aluminium hydride LiAlH4 is going to reduce, say, a ketone, and due to this a secondary alcohol will be formed. Okay, now how will this thing work? So this reaction is followed in two steps. In the step number 1, lithium aluminium hydride, I should write it like this: aluminium, I have already mentioned this structure. Aluminium is attached to 4 carbon atoms. Okay, now I am writing this charge over here. Now H takes away the electron, and obviously H will be acting as a hydride ion. Now this hydride ion, as you know, that it is a nucleophile. Now it can undergo nucleophilic addition reaction with a ketone. Now in ketone, as H negative releases and approaches towards the ketone, due to negative electromeric effect, the pi bond between carbon and oxygen will break and oxygen will take away the electron, and now hydride ion gives its electron to the carbonyl carbon. Due to this, an alkoxide ion is being formed. Okay, so this is RCOR. The hydride ion gets attached over here. Oxygen, because it is having the pi electrons, it gets negative charge, and the lithium over here gets attached to this oxide ion as a counter ion. So now here you get an alkoxide ion. And the rest of the part is AlH3. Now in step number 2, this R, C, O negative, Li positive, H, R is here. This is the alkoxide ion formed in the step number 1. Now this is the part where we do the workup. The thing has been reduced. We just have to get our alcohol. We have to take out from the reaction. For this reaction, we can use water, but care must be taken that it must be added slowly. So water must be added. So what will happen, that oxygen will take away the electron, and this negative ion will attack on this positive ion. So it's a protonation kind of thing, and secondary alcohol will be formed along with lithium hydroxide. So this is step number 2, and this is how LiLH4 gets converted, converts a ketone into a secondary alcohol. This is our product. So this is about the mechanism of LiLH4. Now let's study the mechanism given by sodium borohydride. Mechanism of reduction by sodium borohydride. Now the first step over here is similar to that of LiLH4. So let us take the same example where we are reducing we are reducing a ketone by NaBH4 R C double bond OR, and this ketone gets converted into secondary alcohol RCHOHR. And okay, now in the first step, step number 1, everything happens similar to lithium aluminum hydride case. We are having boron attached to 4 hydrogen atoms having a negative charge. The hydrogen will release as a H negative ion. This H negative ion will act as a nucleophile. It will attack to the carbonyl carbon over here due to breakage of this pi bond, because H negative was coming towards it, and this is known as negative electromeric effect. Due to negative electromeric effect, the pi bond between oxygen and carbon was broken, and H negative ion, hydride ion, attacks to the carbonyl carbon, and it forms an alkoxide ion similar to that of LiLH4. So the sodium ion over here comes as a counter ion, and an alkoxide is formed. Now this alkoxide, in the step number 2, gets a proton from an alcohol. It gets a proton from an alcohol. So alcohol oxygen takes away the electrons, and it accepts a proton and forms RCOH, single bond H and R, a secondary alcohol. And rest of the part, R dash O negative attaches with Na positive, and we get another alkoxide ion. Now you must be wondering that how it happens, why in the lithium aluminum hydride it takes away a proton, and why in sodium borohydride a proton is taken away from alcohol. See, you have to understand the nature of alkoxide ion. Alkoxide ions are usually bases. They are bases. They have a strong tendency to get a proton. So when proton is presented in form of water, it quickly takes it and converts into secondary alcohol. Meanwhile, in alkoxide ion, it's again an alkoxide ion. It takes away proton from the alcohol, because alkoxide ion, okay, it requires a relatively weaker acid, so we are using alcohol, and which is becoming a source of proton and forms a secondary alcohol. So this is the reason why we use alcohol for the reduction, in the reduction process. So this was all about metal hydride reduction. In the next class, we will be dealing with the named reactions. Thank you so much.